I've been trying to do as much as I can on the channel with traditional watchmaking tools, but I really ran into problems with gear making in terms of the traditional tools for it. There's a gear cutting machine, which is this thing that in this plate, let me run a movie of it. This plate at the bottom, you've got all these holes, and you move the little thing with the finger catch there to sequentially to different holes, and that rotates your gear blank, and then you cut it with the kind of lathe mechanism at the top. And those are the way it was done in the old days, but they're quite expensive to get one that's working today. So it's easier if you use a stepper motor like this to rotate the gear to any position that you want. So what I've done is I put a tutorial for how to build this yourself on my website. I make watches under projects, CNC Index Driver. And it's basically, you can build it out of these parts that I have on my desk. So I'm going to build one up real quickly here, hopefully. And you can see all the steps involved. And then if you want to make one for yourself, you can go to the projects page on the website and get the code, because basically it's taking generic parts, hobbyist electronic parts, putting them together, and then there's a Python script that pulls it all together and makes it work. And there are two versions of it. There's a simple, I think it's NEMA 17 stepper motor for a small lathe, like a Boley B8 lathe. That's the motor here. So this is this motor is directly in line with your drawbar and spindle on the lathe, and there's no gearing. And then, but it uses a feature of the stepper motor, which is called micro stepping, to turn it. Most stepper motors 200 divisions per 360, but you can multiply that by 32, so you get like 6,400 divisions per 360, which is enough to do fairly accurate gear teeth. And then this is the box that I made first, one of the first controllers I made, or the first controller. And you can see it has, for this one I cut holes, it has these switches that help you run it. They're push buttons underneath these brass buttons. And then for the version in the project, I changed the design to have kind of 4 buttons that are just machined out of the plastic for the case. So the case is a standard off-the-shelf case that you can order for $10 or so. And then you have to cut out the window for the display and cut the buttons. And the idea behind the buttons is that they're cut all the way through on 3 sides, and then this side is just a shallow cut so that it flexes like a hinge there. And the shallow cut gives us some contour so it looks like a button, but it also allows it to flex a bit. So when you push one button, it doesn't push the other buttons beside it. That's the theory behind that. And then that I'll include some 3D files for this in the download package on the website along with the code, the Python code for the scripting of it. Scripting is just a word for code, basically. And then I did 2 examples of this, one using CNC and one using a watchmaker's lathe to actually, my W12, to cut these buttons. So that's something cool that you can do as well. If you don't have CNC, you can just manually measure and cut the buttons yourself. So a quick aside here about CNC and doing the front plates with the lathe. This is a CNC machine that I've had for a number of years. It's a Carbide 3D Nomad, and it's a 3-axis XYZ CNC milling machine. First, you create your object in SketchUp or FreeCAD or whatever, some kind of CAD program, and then you import it into this program mesh cam for Carbide 3D anyway. So I'm going to reopen the last one I did. And this already has all the parameters in it in terms of, you basically have to select you have to tell it the scale of everything, keep out regions, like what you want to cut, what you don't want to cut. So in this case, we only want to cut what's inside of the object here, not the edges of the object. And that's all been done. And then it will calculate the tool path for you, this program. And if I hide the geometry here, you can see these yellow lines represent what the tool is going to do in terms of cutting, and the red lines are when it moves above the workpiece. So once that's done, you save the tool path to a file called NC, which I think is actually G code. I think that's the name of it in CNC language. But anyway, I'm going to cancel this and I'll just open, because I've already done this. I don't want to mix up which file it is. I'm going to open this with a text editor. So this is like just a bunch of information about spindle speed and paths, XYZ paths, and points. And I'm not sure if it's universal to other machines or not. In one way it is. G code is a universal language, but but it may need to be prepared by your specific software that's associated with your machine. In any case, after that's been prepared, then there's a separate piece of software that actually controls the machine. So what we do with that is we load that same G code, top case cutout new, to, and then we're going to quickly, the machine needs to figure out where needs to kind of orient itself. So it goes to the home position, like it was left in a different position. And then when I click again, it'll measure the tool, and that gives it a very precise Z depth. And then this rapid position menu will let me go to, I've already set the 0 position because I just made one of these. So I'm going to go to the current offset XY and then Z plus 6. So you can see XY brought it to the corner of the workpiece, and then Z plus 6 brings it 6 millimeters above. And I can bring it down until I touch it. If I bring it down 6 more millimeters, so I can say done and then bring the Z down. Okay. So once you've checked or set your origin, you can go ahead and run the project. It stops so that you can insert the tool that you've defined previously in the other software when you set up the G code, because it has to, in order to cut it, it has to know the width of the end mill, because it's going to take that into account in terms of dimensioning. Perfect. So that's the CNC, perfect every time. And then I'll show you the lathe version as well, or quick edit of it. So I'm going to start out by gluing a wax chuck to the front plate that I want to cut. And I've measured it so that I'll place it in the middle of the window that I'm going to cut out, so that I don't end up cutting the wax chuck. And I've already pre-measured and marked all the cutouts. I marked it with a mat knife and that T-square there. So the markings are already on the other side of it. And then I'm just going to check it to make sure that make sure it's square in that window, so I won't cut the wax chuck. And then mount that in the W12 lathe and set up the milling attachment. And this is the same bit that I use in the CNC machine. Should do it. It's a 3.2 millimeter shaft. The spindle is fixed. So I can watch it come out on this side. And then just go. One thing that's cool about doing this is that, of course, this can also be used eventually to mill faceplates or to skeletonize a watch movement or various other watchmaking moves. So this is good practice working on soft plastic because it's easy to cut. And it's also easy to get a sense of how much you really have to be careful about the cross slide tolerances. Like you can tighten the cross slide so that it doesn't move around as much. And as it moves around, you can see that in the cuts afterwards. You can see that the cross slide wasn't tight enough or whatever. So I think this kind of work with the lathe is good practice. that's that cut. And something I did before I did that, I forgot to show on video, is I made sure this is level. Probably can't see that. Yeah, you can. Okay, so that's... Now I can pull this back, flip this around. I think I'm going to have to free it because it's not going to rotate down here. So free it. I wonder if I should just do this one next. No reason not to. So same thing, got to level it. Now, when this cut is done, I don't want it to fall, so I'm going to put some masking tape. So that's the last of the plastic. Looks like they touched. Yeah. Cool. Now, you might ask why I didn't do the buttons using the same technique. And the problem is they're too high up. This milling attachment won't go that high the way I drilled that. So I'm going to have to use faceplate chuck. can use this to hold it once I remove the plastic. Now this kind of, by virtue of its construction, it holds the piece on axis perpendicular to the whatever that would be called, the shaft there. Oh, I put it a little bit too low. So I got to loosen. Now the interesting thing about this, I can tighten this up. And then for this leveling, I can press it down on the bed of the lathe. And then we can test it with the level. It says it's 0. And this cut's going to go all the way through. That'll clean up. That's just little pieces are stuck in there. It just needs a little sandpaper. And let's see. So when you power this up, you get, I just need this numeric keypad. Okay. So if you plug in a screen to this, you get feedback on the screen, and you can also plug in a keyboard and a mouse, and you can rewrite the program yourself or whatever you want to do. This is basically a full computer inside, but you don't need that if you're at your workbench. You don't need the screen at all. You can just use this screen. The screen, attaching a real screen and mouse and keyboard to it will help you learn Python if you want to learn it and understand how it's working, but you don't need that. So the first thing is that all the instructions appear on this e-paper screen, and it says enable numlock on keypad. So that's so that this sends numbers instead of the arrow keys and stuff. And then press button B, which is this one. And then we're going to simulate making 32 teeth. So I'll type the number 32, enter. Now the motor is doing this. It did a backlash reset. So it went one direction and then it went the other direction to take out any backlash. This particular geared head or geared gearbox, reduction gearbox, has a degree or two of backlash, and you don't want that when you're cutting the gear. So what I did was I put this brake. This is just a plate that comes in contact with the back of the center shaft of the reduction gear, and you can adjust the tension on it with these screws. So what it does, there's a lot of torque in the motor because of the gear reduction ratio, so the motor can turn it, but it's not likely that your milling head is going to turn it just cutting the tooth. So the idea is that this is like a constant friction brake. After that backlash is taken out in that preset that just happened, that brake will hold it steady while you use your milling head to cut your first gear slot. And then after you cut the gear slot, you enter the number. It tells you you finished slot 1, enter 1 to continue. So you enter 1 on the keypad, and you'll see it turn 1/32 of a 360 or whatever, so about less than 10 degrees. Now there's also some noise going on. There's a buzzer in here, and there's a beep on the computer. The buzzer is to remind you not to, when it's moving, not to do something with your milling attachment and get caught where it's turning the gear blank while your blade is engaged or working. So it's just like the buzz is a keep out sound. You're hearing a combination of the buzzer inside the box and the motor itself. I'll do it again so you can hear it again. And then at the end, an audio tone is being played, which goes through the screen, the HDMI output, or it will go to the audio output jack on the box. So if you want to have the beep is basically telling you it's ready. You can also attach like a USB speaker. Actually, I'll do that. So the USB speaker goes in the audio jack here. And then I need the mouse for a minute to change the audio output from the HDMI. Right now it's going to the screen. I'll switch it to analog. That means that jack. So then I need to turn this on. So it's using auxiliary input for audio now, so you should hear the beep here when after this next gear. So it says we've just finished cutting gear number 2, so we'll hit 2. That's the motor and the buzzer. Buzzer only. Beep. So that means you can go ahead and start cutting the next gear. And now to escape out of this, because we don't want to do this 32 times, there's an option to type 999 and hit enter, and in 2 steps it'll take you back to 0. So the first step is just preparing, and then it asks you to enter 31 or 32 to be complete. At this point it's just taking it back to 0. Now this is just taking it back to 0. You can hear, again, the buzzer inside, and you can hear the motor. Mostly I think what you hear is the buzzer. The motor vibrates the desk though, so. Okay. Now it's prompting me to, it's asking if I want to go, well, yeah, it's telling you it's complete. It says press button D, and then now it's prompting to ask if you want to start over, end the program, or shut down. So if you're not hooked up to a screen, you can hit shut down. It'll turn off cleanly, and you can put it away. If you enter 1, the stepper motor is still holding everything in tension, and you can start over. You're now at exactly at the 0 position again. So if you wanted to do a second cut, or if you ran into a problem the first time and you stopped halfway through, you could go advance halfway through again and keep going, and you'd have a perfect match with your previous session. But I'm going to hit 0 to shut down. And then put this away. So we'll bring the, we'll do this again after building up this box that I'll be building out of the bare parts. But just before I do that, just to be clear about this, the way this works when it's mounted on properly and powered, the spindle doesn't do anything. So this belt is here just because on the Boley lathe you can't remove this belt without cutting it. So, but it's not going to drive this because the motor is driving it, and the main spindle of the lathe is only being used to set the gear blank position. I have a gear blank in here. Have to turn it that way so you can see it. Why? Oh, I have to turn it 180 degrees. There's a gear blank here, and the motor will turn it, and then this is a gear hobbing blade on the spindle that would actually do the cutting. So the process is the motor turns it 1 gear index, and then you run the motor and run the gear hobbing wheel to cut the slot. So you would set this at the correct height and then run it forward and backward over the gear using this axis. Yeah, so that's how that works. And then one other thing before I start assembling everything, I designed the CNC stuff in FreeCAD. So this is the drawing for this top plate. And there's another thing I made on here that I think is kind of cool, which is this is a stainless steel base for the cross slide. And this cross slide, I got it for like 65 Swiss francs without the milling attachment, but just the cross slide, which is a Lorch, I think. And it didn't have a way to connect, to attach it to the to this style of lathe. Trying to make sure if I take this off, I don't damage it. But basically, I needed a mount to mount this on a lathe, so I designed it in FreeCAD, and then because I don't have CNC to cut steel, I sent it out to I think it was PCBWay in China has a CNC service, and I think it cost about $40 US to have that CNC'd. And the cool thing about that is that, like, this, as you get into watchmaking, there's so much with these old tools that, like, okay, it's great if you can afford brand new tools and everything is complete, but it's almost like that stuff doesn't even exist anymore, brand new. So in this case, being able to design anything that you need and then make it is great. And even if you have a small CNC machine and you can't make big, heavy stainless steel pieces like this, relative to watchmaking anyway, you can outsource it and get it made. So I think that's really cool. I'll probably eventually do some tutorials on how to actually design simple objects like that in FreeCAD. But for now, I wanted to switch to actually assembling this thing. So the first thing is, this is an off-the-shelf case by ModMyPi. It's in 3 parts. There's this riser section in the middle. And then it's designed for Raspberry Pi 3B Plus. So that's a specific model of Pi that fits in this case. And that just snaps into the bottom. And then I'm going to only secure it with 2 screws because it can be secured with 4 screws, but the 2 bottom screw holes need to be reserved for these standoffs that are going to hold the stepper motor board, the next board, at the right height. So first we'll just put in these 2 screws. And then this is the stepper motor hat, which is made by Waveshare. And it comes with 4 standoffs, but we're only going to use 2 of them because basically the header on the left holds it at the right height. And this arrow is pointing to these switches that need to be set at value 1. And then these jumpers come unsoldered. You need to solder those jumpers. And then I'm going to use some Loctite to hold these risers together so that hopefully they don't unscrew as the thing rattles around, because you don't want loose conductors in a box with bare printed circuit boards. I said we're only using 2 of the risers. Actually, I'm using all 4 because I'm using top and bottom. But what I meant is only on one side am I using the risers, because the header itself acts as a spacer on the other side. So this just press fits, but there's a screw head on the bottom of each of those brass risers, and so I'm tweaking it a bit to get it to slip into the hole correctly so it's at the right height. And the risers matter because they're push buttons on the screen. Here's the screen, ePaper hat, also Waveshare. And because it has push buttons on it, everything has to be at the right height for the push buttons to be firmly backed and level relative to the front plate of the case. So there's no particular modification to this hat, this e-paper hat. You just place it on, but it needs to sit on top of those two risers, and one of the risers has a screw hole in it, which again I'm going to use some Loctite so that it doesn't rattle loose. The other riser just touches the back of the printed circuit board, but it's necessary for the stiffness when you push the push buttons, which are on the left side there, my left. And this has already been pre-cut. These slots have been cut with a Dremel tool for the power input and the stepper motor output. The other thing is these spacer washers are necessary to get the top cover, which has the push buttons on it, to the exact correct height. And I think those are 0.8 millimeter washers. So there are 4 screws that hold the box together, and for them to not slip out as I'm layering the stacked aspect of the case, I'm going to put some masking tape on them so I can flip it around and they won't fall out the bottom as I flip it over. And then there's 8 washers total that I'm using, and because there's a plastic riser, I'm putting one washer on each screw underneath the riser, and then I'll put 1 washer on each screw above the riser. And that's just they could both be below or they could both be above, but basically you need that space before that top cover plate goes on so that the push buttons have the right tension. And then I made a pre-cut a piece of polyester tape backed with itself, so it's not sticky in the middle of it. And that's to back the push buttons so that if you get metal filings or something on the unit while you're using the lathe, that'll trap them so that they don't fall through the push button gaps and end up on the electronics. The screen is kind of not protected, but you can see if something falls on the screen and you can wipe it off or tap it off, vacuum it off. And so now the trick is to pull that tape off and then screw the screw in before it slips. I can't talk that fast, so I'm going to have to narrate at the normal speed. Anyway, I put those 4 screws in. The buttons are working, you can hear them clicking. And then finally the SD card. So this SD card has the software on it and the boot. This is like the hard drive for the computer. The boot drive, and already has the software and everything pre-installed. So that's all. It should just be able to be powered up and it should work. Okay, and now hooking this up, the motor comes with a cable that's keyed on the motor side. So it can only go in the way it's supposed to go in on that side, on the motor. And this is called the DuPont connector, and on this side the metal tabs go up and the black wire goes to the left. So enable numlock, press button B. So I'm going to say 32. So the motor did its thing. And then I'll do 1. Two. Now there's one thing about this, which is there, you can hear how quiet this is compared to the other one. I didn't put the buzzer in here. I'll have to put the buzzer in later. And I'm guessing that the audio is not going, oh, the HDMI is not attached. So I would have to get this beep to work, I have to plug it in, and then I'll probably have to change the system setting so that the audio is directed to the auxiliary out. But we'll try this with slot number 3 and see if it beeps when it's done or not. I forgot to turn this on. Okay, one more. Do tooth 4. Oh yeah, so it is set for auxiliary out. So this is without the buzzer, which is an additional part, and it has to be soldered in here. You don't necessarily need that if you don't want that buzzing sound when the motor is turning, or if you don't care. In this case, that cues you that it's done moving. Okay, so, oh, here, this is interesting. Right now the stepper motor is engaged, and it's holding the step wherever it stopped. It's holding it in a position where it doesn't want to rotate. If you force it, you can overcome a NEMA 17 stepper motor, no problem. But basically, this is what I'm saying about it controls backlash. There's no backlash here. Either you break the position or you don't. You don't ever want to break the position when you're actually cutting a gear, of course, but I just want to show you it is possible. But there's a lot of tension. It wants to sit in the position that it's supposed to be locked in, and that includes the microstepping position. Because the way microstepping works is that it alternates the power between 2 coils, and it alternates it in a way that holds it in that microstepped position. But in any case, what I'm going to do now is type 999 on the keyboard so it can go all the way forward. So it's actually going to go through almost the full 360 now, and you can see if there's any tension in the motor, if you hear any strange noises, or if it seems like it's skipping. So this would be a test you'd want to do to make sure that your everything is in line and that your Z shaft coupler is properly utilized so that it smooths out any lack of parallelism in the motor shaft and the spindle shaft. Okay, that's done. I'm going to enter 0 to shut down. So one thing that's cool about this, with the Boley lathe, this setup is, I took a piece of square steel tube and slotted it so that the motor bracket can slot into it on top. And that's a motor bracket like this that's made for 3D printing. So there's a whole kind of Lego style system for 3D printing, setting up things on a grid. So this bracket fits in slots. So I put slots in the tube for the motor, and then I put a slot for this is actually a standard Boley clamp for holding a graver rest. But you can use it to hold down anything. So I'm using it to hold down the rectangular tubing. The other thing, depending on the height of your lathe, you could actually use this 3D printing extruded aluminum shaft and you could use that as a spacer and then figure out some other way to attach it to your lathe bed, particularly if it's not a 20 millimeter diameter rod like this. And then there's also, this is something that's in the links on the webpage, which is a 20 millimeter clamp that you can, it happens to be almost exactly the correct height, if not exactly the correct height, to attach one of these clamps to it. You'd have to drill and tap holes for it, but then you can screw that on, and if you need to shim it or cut it down, file it down a little bit to dial in the exact height, you can do that. But this gets you exactly in the zone also, and then you don't need to use, if you don't have an extra graver rest clamp or whatever, you can just use that. And then the Z-axis coupler is very important because it's really difficult to get these in perfect alignment, and this allows the shaft to bend a little bit X and Y, but Z, it doesn't introduce any backlash. It only allows flex on the two axes that don't matter in terms of backlash. So that's really important. And then this is like 8 millimeter on this side for the 8 millimeter drawbar, and 5 millimeter I think on this side for the 5 millimeter shaft in the stepper motor. And these are also linked in the project page. And then you also have these aluminum hand wheels that are linked in the project page. So the motor has a double-sided shaft, so you need a 5 millimeter hand wheel on the outside, and you may need an 8 millimeter hand wheel if you have a lathe that has a shaft like this and you have to remove your old hand wheel. It's about the same size, so you could just break off the plastic hand wheel and then replace it with this and switch this off when you put the milling attachment on. And for me, my Boley lathe came with, this was the original aluminum handle that came with it, and it was already removable. So that was cool because it gave me this idea of like, well, if you don't have a removable one, you can just make it removable. You can also put some rubber feet on the, let's move this out of the way now. This is just a hardware store item, these little rubber feet. So this is how the buzzer is soldered on. These 3 pins, ground, signal, and positive 5 volts. And I potted this buzzer that had some exposed solder pads on the back. I don't want that shorting on something in here. So I put some epoxy on the back of it, and I put some heat shrink tubing on the leads for the same reason. So I can just drop it in here and then put this display back on. All right, thanks for watching. I hope you found that useful and interesting, and hope that you're able to make your own with those instructions. Thanks a lot.